Okay, so we're going to continue looking at kinematics, more advanced kinematics, but this time, instead of looking at vectors and 2 dimensions, we're going to step back from vectors. We're going to go back to 1 dimension, so essentially making the problem a bit easier, but we're going to change what we know about the acceleration. So previously we were looking at constant acceleration, and if the acceleration is constant, you can use Suvat equations. If we now switch that to variable acceleration, you can't use Suvat equations anymore. Okay, so in one sense, the topic for this video is simpler because it's 1 dimension rather than 2. We're talking about problems that happen in a line, a 1-dimensional line, but the acceleration can vary. That means we can't use Suvat equations. So instead of using Suvat equations, we need to go to our more advanced technique, which is differentiation and integration, effectively calculus. So what I'll be doing is I'll remind you about a few of the rules of differentiation and integration, and particularly as they apply to mechanics, and then we'll look at an example. So there's a few rules to get through, a few reminders really. Okay, the first of these reminders to do with relating displacement, velocity and acceleration. So let's remind ourselves of that. We're going to use S, remember, for displacement, V for velocity, and A for acceleration. Okay, all the stuff I'm about to put on this page is stuff that we have talked about before. It's not new, but it serves as a reminder. So that's our 3 letters we're going to use, and then in brackets next to velocity, I'm going to relate this to displacement. So this is the rate of change of displacement. That's what the definition of velocity is. So you start with displacement, then you take its rate of change and you get velocity, and if you take the rate of change of that, you get acceleration. So acceleration is the rate of change of velocity. Okay, and then mathematically speaking, we can write that like this. We can say V is equal to ds over dt. That's our rate of change. And similarly, acceleration is the rate of change of velocity. And then kind of equivalent to these, we can also say, I'll put double arrows to show it's equivalent, that displacement is the integral of velocity with respect to time. And equivalent to this statement here, we've got velocity is equal to the integral of acceleration with respect to time. Okay, so this one's saying velocity is the rate of change of time. This statement, which is equivalent, is effectively saying that if you take velocity and multiply by time, you get displacement. And this statement is effectively saying if you take acceleration and multiply by time, you get velocity. Okay. But if you're happy with these, these statements here, that's all I really need at this stage. And then of course, you do need to remember that if you actually perform the integral here, you always need to add your constant, your plus c. Okay. So that's the first thing. That's the first reminder. So the second reminder then, it's about integrating trigonometric functions. So let's just make sure we remember how to do this. So I'm going to write integral of cos x with respect to x. In fact, I'm going to do with respect to t, because that's probably more relevant. Let's say cos of t with respect to dt to get you used to the t variable. What is that? Take a moment. You should be happy to say sine t plus c. Okay. Integral of sine t with respect to dt. take a moment. What is it? Should be happy that it's this, minus cos t plus c. Okay, and then stepping up slightly, what's the integral of cos of some constant k times my variable t? What is that? So in this case, we've got 1 over k sine k of t plus c. And the way to convince yourself of that, in case you've forgotten, is I suggest differentiate this right-hand side and show that it ends up being equal to this. And in order to perform that differentiation, you're effectively using chain rule. You're saying the derivative of k times t with respect to t is k. So I multiply, and it cancels out with this 1 over k. And then the derivative sign is cos, so I get cos kt. But that's me effectively stating the chain rule. Okay, and then final check. You need to remember what this is. And it is minus 1 over k cos kt plus c. Okay, so just a quick check, quick quiz. Can you answer these three? The first two are integrals, the third one is a derivative. Can you answer those? You can pause the video now and try. Okay, and what we should get for the first case, 1 over that letter A is constant, sine of AT plus C. And remember, you know that A is a constant because we've said respect to dt, therefore t is the variable, and all the other letters are treated as constants. Second case, we should have 1 over 2 pi minus that cos 2 pi t plus c. And for the final one, we're going to have the derivative of the inside, which is 5, multiplied by cos of 5t plus 3, and no constant because it's a derivative. Okay, cool. Hopefully you got those. If you didn't, remind yourself of how you can get those answers. You're going to have to look back at your differentiation and integration rules. Okay, and then final reminder, there's quite a few reminders here. In year 13 especially, you're going to make a lot more use of radians, okay? And remember, you want to get used to radians. Don't treat them as like some weird, strange way of measuring angles, because radians are in fact the correct and most proper way to measure angles, and degrees are essentially for those people who were never able to get used to radians. Radians make a lot more sense. So let's make sure we're comfortable with the graphs of sine and cos with radians. I'll just do one of them actually. Let's just do sine, because cos is just shifted by 90 degrees, or pi over 4 radians. I got that right? Pi over 4 radians? Make sure you check me. Pi over 2 radians, I should say. Right, sine graph. Can I draw it? Roughly speaking. Okay, that'll have to do. So we remember that when talking radians, this one's 0. And this point, oh, let's do a full cycle actually. A full cycle of the graph is the same as a full turn of a circle. How many degrees or radians are there in a circle? 360 degrees, same thing as 2 pi radians. Okay, let's just make a note up here again. Remember that 360 degrees is equal to 2 pi radians. And then you can multiply and divide that however you wish. So if I had 180 degrees, we've got pi radians. 90 is pi over 2, and 45 is pi over 4, and so on. Right, so then this point here is going to be pi halfway along, over here we've got pi over 2, which is a quarter, and here it's 3/4 along, so 3/4 of 2 pi, that's 6/4 pi, or in other words 3 over 2 pi. Okay, so just make sure you remember that, and remember particularly these conversions, and effectively the factor that you're multiplying by is 180 over pi. So if you've got something in degrees, to turn it in into radians, you're just going to multiply by pi over 180, and that gives me radians. Or likewise, if I have radians, I can multiply by 180 over pi, and I've got degrees. Okay, they're proportional units of measurements, right? It shouldn't be too complex, you know. The only difference between centimeters and meters is one of them is 100 times bigger. Same for degrees and radians. The only difference is one of them, specifically degrees, is 180 over pi times bigger, where 180 over pi is just a number. Okay, cool. All right, so are we done with reminders? Yes, we are. So let's actually get into an example question, and then you can do some of your own. So here we've got a particle moving in a straight line. You're given the acceleration, and it's given to you by this formula. Let's make a note. So the acceleration is equal to cos of 2 pi t, and t is greater than or equal to 0. The velocity of the particle at time t equals 0 is 1 over 2 pi. Let's make a note of that. When t equals 0, v is equal to 1 over 2 pi. Okay, now find an expression for the velocity at time t seconds. So we want to say v is equal to what? Okay, now remember, we can't use Suvat equations. How do I know? Because the acceleration is not a constant. It's a function of time. It changes. It's not a constant number. So what am I going to do? I've got acceleration and I want velocity. If I go back, then this is the thing I want, right? Velocity equals integral of acceleration with respect to time. So let's use that. Velocity is equal to the integral of acceleration with respect to time. So that's equal to the integral of cos 2 pi t with respect to time. And so what's that equal to? Remembering our rules for integrating trig functions. 1 over 2 pi sine of 2 pi t plus c. Okay, let's just make a bit of space. Okay, so we want an exact expression, right? This is almost there, but there's a problem, which is we still have this plus c. But we can figure out what that is by using initial conditions, specifically these ones. So when t equals 0, v equals 1 over 2 pi. Let's work out then what happens. So if I try that, 1 over 2 pi, that's my v, is equal to 1 over 2 pi sine of, now when t is 0, then the 2 pi t will be 0, so it's just sine of 0 plus c. And what does that become? 1 over 2 pi equals, now remember, all of these degrees that we're talking about, sorry, let me rephrase that. All of these trig functions we're using, the inputs are all radians. Okay. Luckily at 0 it makes no difference, because 0 degrees is the same as 0 radians. The output is 0. So we just get 1 over 2 pi times 0, which is also 0, and then it's equal to c. So therefore, we can replace this c. We've just shown that the c is equal to 1 over 2 pi. Okay, and that's our answer. That's our answer for the value of v. Let's make a note of that. Here it is. Okay, the next question is about maximum speed. What is the maximum speed? So to do this, we can actually just consider the expression itself. We've got velocity, it's equal to some expression. And this value of t, it starts at 0, it keeps increasing. So let's just think what's going on with this expression here, this sine value. I'm multiplying it by 2 pi, doesn't particularly matter. No matter what inputs I put into sine, the output is always going to be less than or equal to 1 and greater than or equal to minus 1. Right, this thing, sine 2 pi over t, 2 pi t. So, therefore, this thing, the largest value it can ever take, what's it going to be? The output, sine 2 pi t. It's the largest value in this range, right? And what's the largest value in this range? It's just 1, right? So, therefore, the maximum value for v is going to be equal to 1 over 2 pi, we can't change that, times this maximum value is 1, and then plus 1 over 2 pi, which we can't change either. Which in other words is just 2 lots of 1 over 2 pi, which equals 1 over pi. And therefore, that's our maximum velocity. You could work out 1 over pi, get something like about a third, but keep it just as 1 over pi is fine. Okay, and that's our answer. Let's make a note of that actually. 1 over pi there. Okay, and then the final question is the distance travelled in the first 3 seconds. So in order to do that, let's look back at our little set of equations. We're looking for the distance travelled in a certain amount of time. So look at this one. This is what we're going to use. S is distance, remember, or displacement. If I can integrate the velocity for the duration of those 3 seconds, that will give me the displacement. Let's take this thing then. S equals integral of v. Right. And the thing is now, there's a little trick we can do here. If we know already the specifics about the start time and the stop time, instead of integrating this and getting a constant and then putting in initial conditions, we can just directly use the information about the time as limits of the integral. So the first 3 seconds, what that really means is between the initial time, t equals 0, and t equals 3. That's what we mean by the first 3 seconds. For example, if it was the second, that's annoying use of English there. If it was the next set of 3 seconds, it could be t equals 3 to t equals 6. Well, we're talking about the first 3 seconds, so 0 to 3. What we can then do is put that as limits to the integral. Okay. So from 0 to 3 is the time varying, and I'm integrating the velocity. That will give me the displacement, or even the distance as well, within the first 3 seconds. I guess an important question is the distance and displacement the same in this scenario? Now, if you didn't even make that consideration, you might get lucky and still get the right answer. Sometimes displacement and distance are the same thing, and sometimes they aren't. It depends on if you ever change direction. So if you want to really be rigorous about answering this properly, we should check, does the, what is it we're even talking about here? A particle, does it ever change direction? And even being able to answer that question itself is a skill. How do I know if something's changed direction? What does that mean mathematically? It's changed direction. What it means is that the velocity has gone from positive to negative, or from negative to positive. because in one dimension that is what a change of direction is. It's the velocity, instead of pointing right, it's pointing left now. Or instead of going left, it's now going right. So if we look at this expression for the velocity, ask yourself, is it ever possible for the velocity to change from positive to negative? More specifically, can you ever get a negative value for velocity for this specific expression? And hopefully you can see the answer is no, because sine 2 pi t has a minimal value, the smallest value it can be is -1. So therefore, the minimum value of the full expression would be -1 times 1 over 2 pi plus 1 over 2 pi, which gives me 0. So that's the smallest value the velocity can ever be. It can be 0 for just a moment, maybe, instantaneously 0. So the velocity is actually positive at all times. It's changing, sometimes it's faster, sometimes it's slower, but it's always in the same direction. And just by then considering that expression, we know that for this specific particle, displacement and distance are always the same. The displacement in the first 3 seconds is the same thing as finding the distance in the first 3 seconds. Okay. By default, when we do this kind of integral, what we're actually finding is the displacement. But fortunately, in this case, that's the same thing as distance. Okay. So just be really wary. You've got to always think about this distance displacement distinction, and there's quite a few niche little bits of information you sometimes need to check for. But that's what distinguishes you from someone who thinks about these problems really effectively. Right, so let's actually get on with this integral. So we're going to find the integral of velocity between 0 and 3. What's that going to be? So I'm actually integrating this thing, right? Let's put it in square brackets first. Between 3 and 0, or 0 and 3 I should say, we're going to get 1 over 4 pi squared minus cos of 2 pi t plus 1 over 2 pi t. Okay, so remember, integral of a constant, 1 over 2 pi, is constant times the variable. And in this case, when I integrated this, that 2 pi ended up dividing on the outside. So 1 over 2 pi divided by 2 pi gives me 1 over 4 pi squared. Sine goes to minus cos. That's why I put a minus sign here. Okay. Remember to check your integration rules if you've got a bit lost by that part. And we don't need a plus c because I'm doing a definite integral with limits. So we don't need a plus c. Okay, and then we just need to plug in the numbers here. Plug in 3, plug in 0. I'll just do it on the calculator quickly now and see what we get. Actually, let's not use the calculator. Let's try and do this properly. I'm just going to write this up here. So I'm going to take a constant of 1 over 2 pi on the outside, actually. So then this becomes back to minus 1 over 2 pi. And then we've just got plus t here. Okay. And then if I put 3 into all of that, I end up with minus 1 over 2 pi cos of 6 pi plus 3. And then when I put in, actually let's work that out. Cos of 6 pi, what's that? Well, cos of 2 pi is just 1. Cos of 6 pi, therefore, is also just 1. It's just adding 2 pi another couple of times. Remember, if you do check this on your calculator, make sure you've got your calculator set to radians. Shift and then the menu button, and then set it up so it's doing radians, not degrees. Otherwise, you'll get the wrong answer. But you should know anyway that cos of 6 pi is 1. So in that case, we can actually just get rid of the cos 6 pi there. Okay, plus 3. And then we're going to minus what happens when I plug in 0. That t will just be 0. 2 pi times 0 is 0. Cos of 0 is 1. So it's minus 1 over 2 pi. And I'm going to do minus minus 1 over 2 pi, so I just get plus 1 over 2 pi. So these cancel, and I end up with a final answer of 3 over 2 pi. And that is then 0.477, which is the final answer for this one. Let's write it down, 3 over 2 pi, which is 0.477, roughly speaking. Cool, okay, we've done it. So that's some of the key principles that we need for this particular chapter. Let's then take a look at some questions. I might give you a few hints. Let me just check how many there are again. Just 2 questions for you to do. Have a go at this one first. So you've got a particle moving in a straight line. There's acceleration, which is variable, and it's given to you as a function. Okay. So you want to find the velocity, you want to find the displacement. All you're doing is integrating and then integrating again. But make sure you plug in the initial conditions so you can get those constants of integration. Okay, give that one a go. Pause the video now. Okay, and hopefully you didn't spot it already. There is your answer. Okay, so mainly practicing your integration there, and then using the constants of integration. Next question. So you've got your expression for acceleration here. You've got some initial conditions. Everything is 0 effectively at the beginning, which makes things easy. You're going to find the velocity. You're then going to find the maximum speed. Be careful with the word speed, obviously. Similar to velocity, remember, but if it's maximum speed, for sure, it's going to be a positive number. So what you really want to find is either the most positive velocity or the most negative velocity, and whichever one's bigger, that's your maximum speed. Then you're doing a bit more integration to get displacement. D is similar methodology to part B. And then E, this question in itself implies that there's some funny things going on here. The number of times the object changes direction during its motion. So remember, its motion is between time 0 and 4. So that's its motion, 4 seconds. And the question is, in those 4 seconds, how many times does it change direction? So you really want to think about which equation? When we're talking about changing direction, we want to think about the velocity, right? What does the velocity equation look like? How often does it go from positive to negative in those 4 seconds? So I definitely recommend for E to draw a graph of the V function, the velocity function, and then check how many times does it go from positive to negative, which is the same thing as saying how many times does it cross the x-axis, right? So we're problem solving here. Going from positive to negative, that's the same thing as crossing the x-axis. How many times does it do that? Okay, have a go at that question. You can pause the video now. And there is your answer. Oh, I think I've missed off a few there. Hang on. Okay, there's your full set of answers. Yeah, A, B, C, D, and E.